Welcome back, guys. We're going to take a little break from the math of kinetics and go on to section 12.2, factors affecting reaction rates. So this is everyone's favorite thing with chemistry, theory. Yay! So we're going to describe the effects of chemical nature, physical state, temperature, concentration, and catalysis on reaction rates. It's a pretty short section, but I do have some little videos for us to watch. So the first factor is the chemical nature of the reactant. For example, as you move down the periodic table, the alkali metals react at a faster rate than water. So again, the nature of your chemicals really plays a huge part in the rate of the reaction that takes place. So let's go ahead and watch this.
Here I'm working with some lithium metal, very difficult to cut. I've got a piece of sodium here, pretty easy to cut. You notice when I cut through that the fresh sodium is very shiny compared to the rest. Let's zoom in real quick. Let's see if we can really get in there. So this side will reflect a lot of light. The other sides are pretty dull. And you'll see that especially with the potassium here. I'm going to go ahead and give this kind of a half cut. So for the potassium, this is the side that's freshly cut, and you can see the dullness to the other sides compared to that one. So I'm going to go ahead and take those three, and I'm going to add them to water, and we can look at the kind of reactivity of those three alkali metals with water. So here I'm going to take the lithium and add that to the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off of there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium, so I'm going to put sodium into the next one. And the sodium is actually probably going to ignite. So you'll see some orange flame perhaps, or some sparks, or some shrapnel. And then the last one, I'm going to go ahead and put my two pieces of potassium in that I've cut in half. So this is less potassium than the other two in terms of amount. But you'll find that the reactivity is a little bit greater. Now that potassium there was quite reactive there, but the sodium sometimes will allow hydrogen gas to build up. In this case it's not igniting, but we can try adding another piece here. And we can hope that that's going to go ahead and actually send off some shrapnel and some flame. All three produce hydrogen gas, all three produce hydroxides. There's your alkali metals. Next we're going to go ahead and do the rubidium and cesium.
All right, so pretty cool. If you want to see rubidium and cesium, you can find that later. Whoops. So the next factor is the state of subdivision of the reactants. And what this means is increasing surface area will increase the rate of a reaction. So let's go ahead and watch this video. So now you can see, it was a great video to demonstrate how the rate of reaction is affected by the surface area. You have more surface area, then you can get more contact between your areas, and then poof, your reaction can happen a lot faster. So this is also a picture, there we go, showing you iron reacting with hydrochloric acid. You see that the powdered iron, you can see it reacting a lot more. You see much more bubbles, a darker color in the water, or the acid, if you will. Whereas the iron nail in picture B is a lot bigger. There's not as much surface area for that contact to happen for the reaction, so not as many bubbles and not as much of a reaction. So the next three factors are the temperature of your reactants. So in general, your reaction rate increases with temperature because things are moving faster, you're getting more collisions between the molecules, so they can react faster. Then there's concentration of the reactants. So we're going to look at videos for all three of these too. So you increase concentration, you generally increase your rate of reaction because now there's more stuff for those molecules to hit each other and react. Think of it like going to Disneyland on an empty day versus a crowded day. Probably not my best example to use with it being closed. Nonetheless, going to an amusement park on a day where there's not many people, you don't really have as much of a chance of running into others, no pushing, shoving, or trying to get a spot for the parade. Whereas if you go on a day that it's really, really crowded, people are constantly running into each other, or you're hitting huge lines, having to push and shove just to get a spot for the parade, right? Same type of thing. And then the last thing that can affect your reaction rate is the presence of a catalyst. So a catalyst increases the reaction rate. And we'll talk more about these later in the chapter, so in a different section. So this first video is the effect of temperature on the speed of the reaction. So that reaction was sodium thiosulfate with hydrochloric acid at 2 different temperatures. So you saw that when it was hot, the reaction happened a lot faster. So this next video we're going to see is the effect of a catalyst on the reaction rate. So the chemist here will talk about the reaction he's doing and what's happening. And what I really like about this video is it gives you a bit of a sneak peek about catalysts and how they act in a chemical reaction. And you'll see at the end what I'm talking about.
This is a short demonstration to show how a catalyst increases the rate of a chemical reaction but remains chemically unchanged at the end. In the large beaker, I have a solution of potassium sodium tartrate at about 60 degrees Celsius, to which I'm going to add some hydrogen peroxide solution also at 60 degrees Celsius. The reaction between these solutions produces oxygen gas, so an effervescence will be seen when the reaction occurs. When I mix the two solutions together and stir, there is not much evidence of a reaction occurring at the moment. So I'm going to add the catalyst, which is cobalt chloride solution, which is pink. Please observe what happens when the catalyst is added to the solution. There is a change of colour, and bubbles of oxygen gas and effervescence is beginning to be seen. The reaction is speeding up, and the catalyst is clearly getting involved in the reaction because of the colour change. As the reaction subsides and less oxygen is released, the catalyst is returned to its original state and goes back to the pink solution of the cobalt chloride. So here the catalyst has increased the rate of the chemical reaction but remains chemically unchanged at the end.
So there you have it. The catalyst increases the rate of a reaction, but it's not actually consumed during the reaction. So you saw that that catalyst actually came back at the end. So it doesn't actually take place in the reaction steps or the mechanism itself. It just helps speed it up. So when it comes to collisions, so chemical reactions are the result of collisions between your reactant molecules. So the reactants are hitting each other. They have to do it with enough energy and in the right orientation for that collision to be successful. So when you increase the temperature, things are moving faster, so you have a higher chance of collision. Surface area, you have more areas for them to interact. The chemical nature, that's going to determine how fast the atom or the molecule itself is able to move and interact, or any intermolecular interactions. Concentration, the higher the concentration of your reactants, the more likely your molecules are going to collide and react. So again, a faster reaction rate. But as your reactants get consumed, you're having less collisions and a lower reaction rate, because now you have less collisions happening because, again, lower concentration. So this next video, this is what that link is in the last slide, is looking at the reaction of phosphorus burning in air versus it burning in pure oxygen. So when you put it in that pure oxygen, you're increasing the concentration of reactant, and you're going to see what happens. So as you could see there, when the phosphorus was first lit in the air, you saw a little bit of glowing from it reacting with oxygen in the or just in the air around it, but just a little bit of glowing. But the second it's put in that Erlenmeyer flask that it contains pure oxygen, that flame gets huge and the flask is glowing, right? It's really cool. And then he pulls it out and you see again that flame gets smaller because now you have less reactants. You have less oxygen to react with your phosphorus. Just another example, statues tend to be made from carbonate compounds, like limestone and marble contain carbonate. Um, but over time, what and exposure to the elements, to our weather, water, thermal expansion, contraction, and stuff, it causes them to weather over time. But when we add things like sulfur dioxide, so pollutants in the atmosphere, in our air from manufacturing, driving, etc., this can make the weathering accelerate more. The more air pollutants that we add, the quicker the limestone deteriorates, and the statues don't look as pretty, sadly, anymore.